start this mini lecture by talking about something called the work-kinetic energy theorem. So we have this slide here, but I'm going to show you on the light board how we derive the work-kinetic energy theorem.
And that is going to be a very useful thing for us when we're working through some of our problems for this little section of our class. So we know that the net work is equal to the net force, so that's the sum of all the forces applied, times our direction of motion. So I'm going to call it delta x. That's our change in position. So imagine we have an object, we're pulling on it, the sum of all the forces in the horizontal direction is our net force, and we move it some distance, okay? So work is equal to force times distance, and we're not pulling up at any angle, okay? So remember from Newton's second law, we've got the force is equal to our mass times acceleration. So I can replace the force with mass times acceleration, delta x, okay? Now, let's see. Well, I'm just going to rewrite it like this, ma delta x. We don't really care about that parentheses there. Okay, but there's something interesting about this a delta x here. If you think way back to kinematics, we had this equation that we used and found useful, that the final velocity squared of an object equals its initial velocity squared plus 2 times its acceleration times its change in position. So on the equation sheet, this delta x is x final minus x initial, okay? Let's solve this equation then for a delta x. So divide both sides by 2. We do that. Then a delta x is equal to v final squared minus v initial squared over 2. So I can put this in here where I see a delta x. So then my net force is equal to my mass times what we just found a delta x was also equal to. It's also equal to v final squared minus v initial squared over 2, okay? So I'm going to factor out, well, no, I'm not going to factor out the 2. I'm going to factor through this m, okay? And so then this equals 1/2 m v final squared minus 1/2 m v initial squared. And you saw in your reading quiz this week that the kinetic energy, the energy we have with motion, equals 1/2 times the mass times the velocity squared. So these terms are the same thing as our final kinetic energy of our system minus the initial kinetic energy of our system after we change position, after we move with some velocity. Okay, so this tells us then that our net work equals kinetic energy final minus kinetic energy initial. You can also write this as the change in kinetic energy. This is our work-kinetic energy theorem, that the net work done on the system is also equal to the change in kinetic energy. Okay, the net work done on a system is still equal to F net, the net force applied, times our change in position, but it's also equal to your change in kinetic energy. An object undergoes a displacement and a change in velocity under the action of a constant net force, or a constant applied force. So this is what our work-kinetic energy theorem is and how we can derive it from our very simple work expression that we've been using to this point. Now we're going to apply the work-kinetic energy theorem in order to solve a problem. A similar thing has probably happened to you at some point in your life if you've been involved in a car wreck. I know I certainly have. So we have a driver plus the car with a mass totaling 1 times 10 to the 3 kilograms. That's 1,000 kilograms. And this car is traveling on a road at an initial speed of 35 meters per second. Okay, we'll call that car 1. And it slams on its brakes to avoid hitting a second vehicle in front of it, which has come to rest. After the brakes of this car here are applied, a constant friction force of 8 times 10 to the 3 newtons, that's 8,000 newtons, acts on the car. So that friction force is opposite our direction of motion. Here is our direction of motion, okay? So, using our work-kinetic energy theorem that we just derived, we want to find the minimum distance the brakes should be applied on this car in order to avoid a collision with this other vehicle, okay? So we'll apply the work-kinetic energy theorem in order to find this distance. Remember our work-kinetic energy theorem, the net work done in the system is equal to our change in kinetic energy, okay? So that's equal to 1/2 mv final squared minus 1/2 mv initial squared. That's our change in kinetic energy. Well, our final velocity is going to be 0 because we want to come to rest, okay? So our final velocity is 0. Our initial velocity is going to be our 35 meters per second, okay? And what is this net work right here, okay? We've done this in a similar way in previous problems that we've worked with work and friction. So this net work here is going to be our applied force, which in this case is only the force of friction. So that's going to be our friction force times the distance over which that force is applied. This is the thing we're trying to solve for, times cosine theta, where this angle is the angle between our direction of motion and the direction in which the force is applied. And remember, so direction of motion, force of friction is applied opposite that. That angle is then 180 degrees. So this would be cosine of 180 degrees, which we know to be -1. So we've got minus our force of friction times that stopping distance that we're trying to solve for equals 1/2 times the mass times our initial velocity squared, okay? So we have an initial velocity where applying the brakes, we've got a friction force that's doing work in the system. We're changing our kinetic energy, and the distance over which we are slowing down, the distance over which our energy is changing, is this distance here. That's what we're trying to solve for. That's the distance over which we start from some 35 meters per second and end with some 0 meters per second, taking into account friction, okay? So we couldn't do that with our kinematic equations, but we can do it here by thinking about energy and work. So now we solve this equation for D. Oh, and I lost my minus sign over here because there's minus 1/2 mv initial squared. There's a minus sign there. But we've got a minus sign and a minus sign on both sides, so those are going to cancel with each other. And we find that our distance we need to stop equals the mass times the initial velocity squared over 2 times our force of friction. And so we plug in our numbers. That's our 1 times 10 to the 3 kilograms times our 35 meters per second squared divided by 2 times our force of friction, which was kindly provided for us, 8 times 10 to the 3 newtons. And then that turns out to be 76.6 meters is the distance away from the stopped car that we need to apply our brakes in order to avoid hitting and smushing up that car.
Every system in nature has a quantity we call its total energy. When I talk about a system, just take anything around you and draw a boundary around it. Everything within that boundary you can call your system. The total energy of this system is the sum of all the energies present inside that system. and energy can be transformed from one type of energy into another type of energy within this system. Energy is the currency of our universe. There are some important forms of energy that we are going to be talking about in this class. Kinetic energy, which is energy from motion. Gravitational potential energy. If it's a potential energy, it's energy that is stored and it's associated with an object's height above the ground. So when you think about potential energy, it's energy that has the potential to become some other type of energy. We have elastic or spring potential energy. This is the energy that can be stored when a spring is either stretched or compressed. Thermal energy is the sum of all the kinetic and potential energies of all the molecules in an object. You can have chemical energy and nuclear energy too, but we're not really going to talk very much about these later ones. We're going to focus mostly on kinetic energy, gravitational potential energy, and spring potential energy, and eventually rotational kinetic energy. Gravitational potential energy is an energy that has the potential to be turned into another type of energy. And the gravitational potential energy is proportional to the change in height of an object above the ground. So gravitational potential energy is just our mass of the object times its gravity, so that's its weight, times height, times its height above the surface. The work done by gravity is negative the change of its final potential energy minus its initial potential energy. So let's think about this. If we are dropping an object from some height above the ground and letting it go and it's falling to the surface, okay, our initial height above the ground is non-zero, okay, that would be y initial. Its final height above the ground here would be 0. So in that case, if I'm letting an object go from some height above the ground, this mgy initial quantity is non-zero, but this mg final quantity is 0. So in that case, the work done by gravity is minus a negative number, and then it becomes positive. So when you're letting an object drop from some height above the ground to the ground, the work done by gravity is positive, okay? But if you're moving an object from the surface of the earth to some position higher above that, then the work done by gravity is actually negative. You're doing work against gravity. You have to do work against gravity in order to move that object from the surface of the earth to some higher position above the surface. With that in mind, I'm going to ask you for this engagement check to rank in order from largest to smallest the gravitational potential energy of all of these balls here. Okay, so the number is just the number of the ball. Ball 1, 2, 3, 4, okay? Haven't provided you with any value to represent the height above the ground. You can make one up if you want to. And just remembering that the gravitational potential energy is mass times gravity times its height above the ground. Rank in order these 4 balls for the ones that have the largest gravitational potential energy down to the ones that have the lowest gravitational potential energy. We talk a lot about conservation of energy in physics. It's really important in physics, this idea, or conservation of anything really is really important. When a physical quantity is conserved, that means the numeric value of that quantity remains the same throughout the physical process. So if we assume that all forces acting on the system are conserved, the numerical value of those quantities remain the same, then the sum of the kinetic energy and all potential energies will also remain constant at all times. So this equation here is our equation for conservation of mechanical energy. What it's saying is that within any system, the initial kinetic energy plus the initial potential energy of the system at some time has to equal the kinetic energy plus the potential energy at some later time. Okay, and so usually we write it as the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. You could choose an initial to be at any point in time or space, and you could choose the final to be at any point in time or space. So if you're thinking about the energies in the system between a point A and a point B, you could choose A to be your initial condition and B to be your final condition. Potential energy is the energy a system has due to its position, shape, or configuration. It is stored energy that is completely recoverable. You store that energy, you can convert it into kinetic energy, and you can bring it back again. We also talk about conservative forces. A conservative force is one for which work done by or against this force depends only on the starting and ending points of a motion and not on the path taken. So imagine you're on a roller coaster. You start over here at point A, and you do a bunch of loop-de-loops, you go upside down, you make a bunch of curves, and then you end, over here at point B, okay? It doesn't matter the path that I took if my energy was conserved. All that matters is where did I start and where did I end? And we can define a potential energy for any conservative force. We are going to use this idea of conservation of mechanical energy in order to solve a problem here, and I'm going to work through it on the light board. If you see me talking about mechanical energy, that's energy that's associated with kinetic energy and potential energy.
I think you're really going to like conservation of energy. It's a much easier way for us to solve similar problems that we've been using kinematics to solve and that we've been using Newton's second law to solve. So here in this problem, we have a 0.4 kilogram mass bead. And this bead is sliding along on this curved wire here, kind of like a roller coaster, okay? It starts from rest here at point A. So our initial velocity at point A is 0 meters per second, the initial, okay? And it's going to slide down to B and then up to C. If our wire is frictionless, we're going to find the speed of our bead at point B and at point C using conservation of energy. Okay, so let's find our velocity at point B. Okay, so conservation of energy, we have our initial kinetic energy plus our initial, we'll call it gravitational potential energy, equals our final kinetic energy plus our final gravitational potential energy. Okay, so let's see, this is 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. Now we can go ahead and get rid of some of these terms, okay? We are going from point A to B, so we're going to do conservation of energy between point A and B. At point A, we know that our velocity is initially 0, so our initial kinetic energy must also be 0 if we're not moving. And then when our object gets to point B, we have no gravitational potential energy because we're sitting on the ground, we're not raised any distance above the ground. So our final gravitational potential energy is 0. And already we can see that the mass is going to cancel on both sides too. So we've got gravity times our initial height equals 1/2 v final squared. So we're just going to solve for v final. So I can multiply both sides by 2. When I do that, we get rid of this 1/2. Okay, so we've got v final squared equals 2gh initial. So square root both sides. If we take the square root of both sides, then we'll see that v final is equal to the square root of 2 times our acceleration due to gravity times our height above the ground. So that's equal to the square root of 2 times 9.8 meters per second squared times 5 meters was our initial height. And so that gives us a final velocity at point B of 9.9 meters per second. All right, easy. And now let's find our velocity at point C. v at c. Okay, so there are a couple of different ways we can solve it. We could do, there's two different ways we could solve it. Doesn't matter where we start from. We could start from point A and use that as our initial condition for initial kinetic energy, initial potential energy, or we could use point B to give us our initial kinetic energy and our initial potential energy. I don't know if one of those is easier than the other, so since we've already used point A, to find our velocity at point C, let's go from our initial kinetic energy and potential energy at point B and our final kinetic energy and our final potential energy at point C to solve this problem. All right, so we'll have our initial kinetic energy, which is 1/2 mv initial squared, plus our initial potential energy, mgh initial, equals our final kinetic energy plus our final potential energy. And so remember, we're going from points B to C here. Up here we did from points A to B. Okay, so if we're using point B as our initial kinetic energy and potential energy, we are sitting at the ground. So we have no initial gravitational potential energy. This height above the ground is 0. Okay, but when we reach point C here, we have a non-zero final velocity, and we will have a non-zero height above the ground. So nothing on this side of the equation cancels. But our masses do cancel again on both sides. Masses cancel here, 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 so we don't even need the mass of our object at all. So we're solving for the velocity at C, so we need to get this final velocity by itself somehow. So we have 1/2 v initial squared. I'm going to subtract this term over to the other side, okay? Minus g h final equals 1/2 v final squared. Okay, now we've got these halves floating around. Let's get rid of them by multiplying both sides of our equation by 2. Multiply both sides of our equation by 2. 1/2 times 2 is 1. 1/2 times 2 is 1. So we've got v initial squared minus, we factor that 2 through these parentheses, so 2 times 1/2 is just 1. And then we've got minus 2gh final equals v final squared. Okay, so now we just square root both sides. And so then v final is equal to the square root of v initial squared minus 2gh final. And remember, for this problem, B is our initial condition, C is our final position. So we can use, for our initial velocity at point B, well, we already calculated that. That's the velocity we found from our previous problem, okay? That's the velocity that our ball has at point B, which we're using as our initial condition for this second part of the problem. So this initial velocity would be our velocity that we have at point B, 9.9 meters per second, squared, minus 2 times 9.8 meters per second, and then I've labeled over here at point C, we're a height 2 meters above the ground. Okay, 2 meters. So plug all that in, we get our velocity over here at point C is 7.7 meters per second. Okay, if we're conserving energy this whole time, then I'm going to have a smaller velocity here at point C than I do have here at point B. If I'm moving from A to B, I'm converting all that potential energy to all just kinetic energy down here. Okay, so that's why my velocity is so large at point B. And then I'm taking all that kinetic energy and I'm converting it, and over here at point C, some of that kinetic energy, that was all kinetic energy at point B, some of that goes to kinetic energy at point C, and some of it goes to gravitational potential energy at point C. Okay, and so that's why our velocity is greater down here at point B than it is up here at point C. And if I were able to come all the way back up to 5 meters, then my velocity there at that height would be 0, because I would have, again, converted all of this kinetic energy back to only potential energy.